Okay, now we're into section 5.5, and we're going to look at this is all about the modulus of a complex number. And we can call it modulus. We could call it the norm. We could call it the absolute value. Now, some might get upset with a couple of these at times, but if we have z equal x plus iy, then the modulus or norm of z, or absolute value of z, using lines like that, is the square root of x squared plus y squared. So now this is really starting to look a lot like vectors and so forth, right? And again, we had the geometry thing. So, if I'm out here at some x and some y, there's the y-axis, there's real. Then, right, what's this distance? This distance is the square root of x squared plus y squared. Okay, so it's really just the distance formula from the geometry standpoint of complex numbers. And if we want to get the distance between two complex numbers, or the absolute value between z1 and z2, well, it is simply that same kind of distance formula. So that's x1 minus x2 squared, so the real parts, plus y1 minus y2, okay, the imaginary parts. And it's just the regular distance formula between 2 points in a plane. So nothing amazing there. Now, what's very nice, though, is remember that well, let's look at, if I take z squared, the absolute value squared, then I just get x squared plus y squared, right? Because there, just square that. But we've already seen that that's z times z bar. So that's nice. And then there are some other properties. Property 1, the absolute value of z1, z2 is what you would hope it would be. It's the absolute value of z1 times the absolute value of z2. And, that's probably, if I were going to prove that, I would probably do it with the squares, I think, and do it that way, and then say, well, then I could take the square roots. As long as z inverse exists, the absolute value of z inverse is the same thing as the absolute value of z, and then take its multiplicative inverse. So again, all these absolute values, those are real numbers. Here, that is not a real number yet, but then once I do this, then I'm just talking a regular multiplicative inverse at that point for real numbers. 3, again, if I'm doing a division, I can do that either the absolute value outside the division, or I could do the absolute value first and then do the division. Yeah, okay, so I hadn't quite scrolled down that far, didn't remember. That is how they prove number 1. They go ahead and do a proof of 1. And they indeed look at z1, z2 squared, like that, the absolute value squared, because then I can just say, oh, that's z1, z2 times z1, z2 complement, but I can separate a complement conjugate, sorry, I can separate those conjugates, and then I can rearrange things and get Z1 conjugate, and Z2 conjugate. But now that's the absolute value of Z1 squared and the absolute value of Z2 squared. So doing the square, usually when you don't have a square root, it's easier to deal with. And so, it's, I kind of like their example, I guess. So they give this example, 5.5.1, and they say, oh, okay, here Z is 1 plus I to the 4th over 1 plus 6I times 2 minus 7I. And they say, hey, find its absolute value. And, so the absolute value of Z, well, I can immediately go to nicer things. I can say 1 plus I inside the absolute values to the 4th, and over 1 plus 6I, absolute values there, and absolute values of the 2 minus 7I. So I don't have to multiply all that stuff out to begin with. And then the top, x is 1, y is 1, so I get 1 squared plus 1 squared, all to the 4th. And then here I get a 1 squared plus 6 squared, and then a 2 squared plus 7 squared, or negative 7 quantity squared. And so this is square root of 2 to the 4th, so that's actually 2 squared, all divided by the square root of 37 times the square root of, 49, and 4 is 53. And so I get 4 over the square root of 37 times the square root of 53. So there we go. There's an absolute value with complex numbers.